Welcome everyone to week 5, part 2 of heat and thermodynamics. I recorded this late last night and I didn't have any audio, so I'm going to try this again and hopefully get you through. Just so that you know, this video is going to be kind of long. I'm going to go through 4 different calculations. The last 2 I'm going to go through, I'm going to have you try to do them on your own, and then I'll work through them step by step at the very end of the video. So if you're good with those 2, feel free to not watch the entire video, and just kind of, that's my excuse for this being as long as it is, but I'll try to keep moving. So the idea this video is we're going to go through and we're going to solve for that final temperature when we have 2 or more objects that are reaching thermal equilibrium. But now we have phase changes this week, right? Because last time we didn't have phase changes, so now we're going to have phase changes. So review stuff, identical from the previous slides. So when we have phase changes, we have a phase change, we got to get this plateau, and we have to go, is it the plus or is it the minus? Is it latent heat of fusion or is it latent heat of vaporization? Those are some choices we need to make, but because they are thermal equilibrium problems, we're going to say the sum of all my Q's is equal to 0, and that's what we're solving for. How do we draw these? This is the steps that we use when we draw them. We have a maximum temperature, we have a minimum temperature. We put the temperature of our phase change. We have to decide whether it's LF or LV. We have to decide whether that's going to be the positive or negative. And then we're going to draw this line for my final temperature. And then we draw in our lines with our arrows to determine the number of Q's in our system. So how do we know, again, which equation? We are dealing with 2 or more objects that are reaching thermal equilibrium. So we're using the sum of all my Q's is equal to 0. And we're going to be adding them all up. Whereas if we only had 1 object, we'd be solving for how much heat was gained or lost. Just quickly, remember latent heat of fusion is when we go from solid to liquid. Latent heat of vaporization is from liquid to gas. How do you know whether it's the plus or it's the minus? It's the plus or it's the positive when energy is being added or your arrows are moving to the right on the map. It's negative when the energy is being removed or it's moving to the left. Negative is when things freeze or condense. It's positive when things melt or evaporate. So let's get to an example. So when we go through and we set up these problems, we got to start by drawing a map. And that's what part 1 of this week's lesson was about, is drawing these maps. So every morning I have a cup of coffee and it's too hot for me to drink, so I put an ice cube in it. So if I have 0.05 kilograms of ice at negative 10 degrees Celsius and I place it in 0.5 kilograms of coffee, draw a map, how many cubes? But the question is, what is the final temperature of my object? So a couple things. We have ice at that temperature, so we have ice. And remember, when we talk about water, we're talking about the melting points and or freezing points. And then we also have coffee. Now, if you notice, the specific heat of coffee is essentially water, because that's really what it is, right? It's just flavored water. So when we go through and we draw our map, the exact same way we've done in the past. We put our minimum temperature of minus 10 degrees. We put our maximum temperature of 85 degrees. Somewhere in between, there is going to be a phase change. And in water, the ice is going to go through a phase change at 0 degrees. And we know that because the melting point is 0. So then we have to decide, is that latent heat of vaporization and fusion? And this is going to be latent heat of fusion. And then we have to kind of decide, is it the plus or is it the minus? When ice is input in coffee, is it going to be gaining heat or is it going to be losing heat? And hopefully you recognize that ice is going to be gaining heat. It's going to have a positive. It's going to be increasing in temperature. So then they're going to meet somewhere in between at something that we're going to call TF. Then we can go through and we can put our initial dots, our temperatures of my ice down here. We can put the dot up here because this is where my coffee is going to start. And then we can go through and we can draw our arrows. So that's going to be my Q1. That's going to be my Q2. That's my phase change. Then we have a Q3. Then lastly, we have our Q4. And they're going to meet right here at that final temperature, that TF. So we are using this equation because it's the sum of all my Q's is equal to 0. It's a thermal equilibrium problem. So when we go through and we start setting this problem up, we can say the sum of all my Q's is equal to 0. And then really what the sum of all my Q's is really just saying is Q1 plus Q2 plus Q3 plus Q4. That's all equal to 0. Now, what's going to happen is we're going to go through and we are going to, I'm actually just going to move that over there in terms of space. We have to go through and we have to look at each Q and we have to say, for Q1, is it a temperature change or is it a phase change? For Q2, is it temperature change or phase change? Q3, Q4. Okay, so we need to make those choices. So temperature change, phase change, temperature change, temperature change. So when we go through and we kind of break Q1 down, it's going to be M1, C1, delta T1, where M is the mass of object 1 at Q1, C is the specific heat of that object at Q1, delta T1 is the change temperature of Q1. And then we can go, well, Q2 is a phase change, so it's going to be plus or minus, and we've already identified it's going to be the plus. It's M times L, and we've already identified that it's latent heat of fusion. So this is going to be plus M, I'm just going to call it M2 times LF. Okay. Then we can look at Q3, and that's going to be a temperature change, so it's M3 C3 delta T3 plus, then my Q4 is going to be M4 C4 delta T4, and that's all equal to 0. Now, again, all these, like M4 just means it's the mass of the object for Q4, it's the specific heat at Q4, it's a change in temperature at Q4. That's all those numbers represent. So let's start putting some numbers in. So what is my mass at Q1? Well, Q1 is my ice. Okay, so it's my ice heating up. So the mass of my ice cube is 0.5. My specific heat of that ice, now it is in the ice state, so it's 2090, times my final temperature. Now, my Q1 is from here to here. So my final temperature is, because it's final minus initial, delta T is final minus initial, is 0 minus a negative 10. That's my Q1. Then we can go plus 0.05 times my latent heat of fusion, which is 333,000. Then plus my Q3, which is the mass of my ice cube. But now my ice cube is from here to here at Q3, and it's now in liquid water form. And then it's my final temperature of Q3, which is my unknown of TF minus 0. That's my Q3. And then we can go plus, and I'm just going to go right down here for Q4. Now we have my coffee, and my coffee has a mass of 0.5 times the specific heat of 4,186 times my change in temperature, which is the thing we're solving for, TF, and that's going to be minus the temperature at which it started at, and that's going to be that 85 degrees, which is equal to 0. So now we go through, we start doing our multiplication, and Q1 is 1045. Q2 ends up being 16650. Q3 is 209.3 times TF minus 0. We're going to have to distribute that in just a moment. Plus 2093 times TF minus 85, which is equal to 0. And for those of you paying attention, sorry I changed my tone of purple. Then we can go through, I don't want that color. We can, I'm going to just rewrite my other terms. Now what we're going to have to do is we're going to have to distribute. So we're going to take 209.3 times TF and 209.3 times 0. And then we're going to take 2093 times TF and 2093 times 95. So we're going to distribute those terms. So we're going to get 209.3 times TF and then times 0. So this is going to be a minus 0 plus 2093 times TF and then minus 177,905, which is equal to 0. I'm going to combine all my TFs, which are written in red, and we get 2305.3 times TF. And then I combine all my non-TF terms, which are written in green in the previous line, of negative 160,210, which is equal to 0. Now, what's going to have to happen is I'm going to move this to the other side, and this is minus 160,200, so I'm going to add, and I have kind of gone through, and I've just kind of say, hey, look, I can just go and say, oh, look, that equals. So then we can go through and we can divide both sides by 2,305.3, and we get a final TF that is equal to 69.50 degrees Celsius. Okay, so it meets somewhere in the middle. My coffee cools off while the ice cube melts. Okay, so that's how we do one of these problems. Very similar to the previous one, we just got to deal with a phase change now. So here's our Q2. Example number 2. So we have steam that we're going to bubble up through the water. And really the intent of this is just trying to say, I'm going to take some really hot steam and I'm going to transfer that into liquid water. And what's going to happen as a result is I'm going to increase the temperature of that liquid water that starts at 10 degrees. So we start with our map. Maximum temperature 120, minimum temperature of 10. There is a phase change that occurs of water at 100 degrees, right? We get water boiling, so that's going to be my latent heat of vaporization. And we can talk about whether it's positive or negative in just a moment. And then what happens is they are going to meet somewhere in between at something that we're just going to call TF. And then we can go through and say my water starts there, my steam starts there. So what happens to my steam? Well, my steam first needs to cool down. We're going to call that Q1. Then what happens is my steam goes through a phase change. And my phase change looks something like this. Now, we've identified that's latent heat of vaporization because it's at the 100-degree phase change. It's not technically boiling, it's actually condensing now. But we are removing heat from the steam, so we need to keep in mind that this LV is going to be a negative number, and that's going to be our Q. That's going to be my Q2. Then we can go through and we can say that steam that's now liquid water is going to cool down to Q3, with the last step is that water that starts at 10 is going to heat up to Q4. So this is a sum of all my Q's is equal to 0, and we can say Q1 plus Q2 plus Q3 plus Q4 is equal to 0. Now we have to go through for each of our Q1s and say, is it a temperature change or is it a phase change? So Q1 is a temperature change, so it's going to be M1 C1 delta T1. Q2 is a phase change, and Q2 is a phase change, and we've already said it's latent heat of vaporization, and it's going to be negative. So when we say it's plus or minus, we need to then, I'm going to change this to red, it's going to be minus, just to kind of draw attention to that, mass times my latent heat of vaporization. Then my Q3, we can call that L2, M2. Then my Q3 is M3 C3 delta T3, because that's a temperature change. And my Q4 is also temperature change, so those M4 C4 delta T4. And that's equal to 0. So plugging in numbers, 0.5, that is steam. Okay, so my steam, my C of steam is 2010. Times from here, my Q1 goes from here to here. So it's my final temperature of 120 minus 100 minus my mass of my steam times the 2,260,000, because that's my latent heat of vaporization, plus the mass of Q3, now Q3 is from here to here, so that is going to be 0.5 times liquid water of 4,186 times the final temperature minus what my liquid water started at in this particular Q3, which is 100. And then Q4 is going to be the 3.5. That's liquid water, so it's 4,186 times the TF minus what that liquid water started at, which is minus 10. And then that's all equal to 0. So now we start going through. Q1 is going to be negative 20100. Q2 is going to be negative 1130,000. Q3 is going to be minus, nope, it's going to be a plus, sorry. It's going to be plus 2093 times TF minus 100 plus my Q4 is going to be 14651 times TF minus 10, which is equal to 0. Okay, so then we can go through and we are going to distribute from here and here. Okay, so we're going to do that distribution. So that's going to be plus 2093 times TF minus 209300 plus 14651 times TF minus 14651, which is equal to 0. Okay, so now we combine our like terms, which are all the orange terms are like terms, all the red terms are like terms that have TF, so we're going to combine our TFs, and we end up with 16744 times TF, and that's going to, then we combine my orange non-TF terms, and that's going to be minus 1505910, which is all equal to 0. So how do we get negative, what is that, 1,505,900 to the other side? Well, we add it, so then that becomes an equal sign. And then we can go through and we can solve for TF, and we get a final TF of 89.94 degrees Celsius. Okay, so that's how we do these. Now I'm going to have you try this problem. So example number 3. First, start by drawing a map, and then when you're done, unpause your thing. So read through the problem, draw a map. I'm sorry, let me rephrase this. Pause it, read through the problem, draw a map, unpause it, and we can look to see if your map is right before you move on. All right, so this is what your map should look like. You should have 4 Qs. You have a minimum temperature of 80. You have a maximum temperature of 220. And then what happens is we get temperature change, phase change, temperature change. We get a temperature change. So there's 4 Qs. So hopefully that's what you have your map. Now, I've already identified that this phase change is going to be latent heat of vaporization. And because my arrow is going to the right, is going to be a positive. So when we go plus or minus in that Q2, it's going to be plus M times LV. Okay, so now I'm going to ask you to pause it and solve for your final temperature of the system. So once you've gone through and you solve for this, hopefully you get a TF of 102.97 degrees Celsius. So my water will have boiled, and then that steam will have increased a couple more degrees. Okay, so if you got it, awesome, great job. If you didn't get it and you say, oh, I screwed up somewhere, where did I screw up? Hang on, I'll go through this problem number 3 at the end, step by step for you. But I'm just going to move on to problem number 4. But if you need to go through step by step with number 3, by all means, stick around. So here's the last example, and we're going to do it very similar. So go through, read through it, and then when you're ready, unpause it after you've drawn your map. All right, so this is what your map should look like. You should have your ice at -15. You should have ethanol at 20. What's going to happen is that ice is going to heat up, and then it's going to phase change, and it's going to heat up again, and that ethanol is going to cool down. So we have a total of 4 Qs. I've identified that my ice is going to go through a phase change called melting at Q2, and it's going to be a latent heat of vaporization. I'm sorry, a fusion, latent heat of fusion. And because of the arrow going from left to right, it's going to be positive. So when you say plus or minus M times L, it's going to be the plus. Okay, so now go through and solve what is the final temperature of the system. When you have it, hit unpause, and we can see if you got it right. So you should have gotten a final temperature of 4.32 degrees Celsius. If you did, great job. You are ready to move on to the homework called Solving Thermal Equilibrium Problems with Phase Changes, and it's posted in Canvas. This quiz is going to be very similar to last week's. We're solving for TF. If you didn't get that, stick around and we will go step by step through problems number 3 and problems number 4 with you. So some of you, have a great day. For the rest of you, let's go through problems number 3 and problem number 4. So problem number 3 looked like this. We had water at 1.5 kilograms at 80 degrees, and as liquid water is poured into an aluminum bucket at 220. So we have aluminum, and we started with liquid water. Now we are going to go through the phase change of boiling or condensing at 100 degrees, so we need to use the latent heat of vaporization. So the sum of all my Q's is equal to 0. We can say Q1 plus Q2 plus Q3 plus Q4 is equal to 0. That's why identifying the number of Q's is important, is because we need to know how many things we're going to add together. So then we can go through and we look at each of these and we say, is Q1 a temperature change or a phase change? Is Q2 a temperature change or a phase change? Is Q3 a temperature change or a phase change? Is Q4 a temperature change or a phase change? And then we can go through and we can say, well, Q1 was a temperature change, so it's M1, C1, delta T1. Q2 was a phase change, so it's going to be M times L, and we've already identified it to be positive. That's why I put a plus sign right there. So it's going to be plus M2 times latent heat of vaporization, plus M3 times C3 times delta T3, because at Q3 that's a temperature change. Q4 is another temperature change, so we can say M4 C4 delta T4, and that's equal to 0. So starting with Q1, that was my mass of 1.5. It starts in as liquid water, so the specific heat, or my C value, is 4,186, times my final temperature. It stops being Q1 at 100. So it's 100 minus, what did Q1 start at? It starts at 80. My Q2 was M2, so 1.5, times my latent heat of vaporization, which is 2,260,000, plus my Q3, which is 1.5. Now that is no longer water. It is now steam, because I'm above that 100 degree mark. So it's 2010 times my final temperature, TF, minus what my Q3 started at, which is at 100. My Q4 is now my aluminum block. Now, why is that massive aluminum so high? It's so we could actually get through these, so we can actually drive this water all the way through the phase change. It has to be very massive, because it has to have a lot of energy. So 33.5 kilograms, which is like 60 some pounds of aluminum. But we can go that 33.5 times the specific heat, which is 899, times our TF of aluminum, minus what the aluminum started at, and it started at 220 degrees, which is well below, keep in mind, the melting point. So we can set that equal to 0. So algebraically, we start setting this up, or solving, I should say. We get 125,580 for Q1. We get 3,390,000 for Q2. For Q3, we're going to have to do some distribution here in a second, but we get 3,115 times TF minus 100 plus, what is that, 30,116.5 times TF minus 220, which is equal to 0. We're going to distribute. So we're going to take this times TF, and we're going to get 3,015 TF. And then we're going to take 3,015 minus times 100. It's going to be a minus. So it's going to be minus 301500. Then we're going to have to distribute this, the 30,116.5 times TF. And that's going to be 30,116.5 times TF minus 6625630, which is equal to 0. Combine all of our TFs, all the red numbers, and we have 33131.5 times TF. We combine all my non-TF numbers, which are the blue numbers, and we get 3411550, but that's going to be a minus because they are, because when you add them all up, you get a negative number, and then that's going to be equal to 0, and it's really because of this aluminum piece right here, which is so big of a number. And then we can move this negative 3,411,550 to the other side. So this becomes an equals. And then we can go through and we can divide both sides by TF, and we get 102.97 degrees Celsius. So that's our Q3. If you're good, go to your homework. If you want me to work through number 4 with you, stick around, because here is number 4. So this is the last one we're going to work through together. So we have a piece of ice, put in some ethanol. So we have ice down here, we have ethanol up here. We note that we have ice, we have a phase change that's going to occur right here. We have ethanol, but notice how we are well outside the melting point or the boiling point of ethanol. So we're good there. We don't have to worry about that. Okay, so now what we can do is we can start setting up. We could say the sum of all my Q's is equal to 0. And what that means is that means Q1 plus Q2 plus Q3 plus Q4 is equal to 0. And then we say, is Q1 a temperature change or phase change? Is Q2 a temperature change, phase change, and so on and so forth. Okay, I did go through and I said, hey, my ice is going to melt, which means it's a latent heat of fusion. And because my arrow is going to the right, it's going to be a positive. So when we say plus or minus M times L, it's going to be the plus. Just keep that in mind. So Q1 is a temperature change, so it's M1 C1 delta T1. Q2, I said, was a phase change, so it's going to be M times L, and I've already identified that it's a latent heat of fusion, and I said as a positive, and that's why I put that positive or that plus sign right there. So then we can say Q3, that was a temperature change, so M3, C3, delta T3, plus Q4 is another temperature change, so it's M4, C4, delta T4, which is all equal to 0. So now we can start plugging numbers in. My ice cube was 0.25 times my specific heat of ice, which is 2090, times my final temperature of Q1, which is 0, minus what my Q1 started at, which is a negative 15. My Q2 was the ice, so 0.25 is my mass, times the latent heat of fusion, 333,000, plus 0.25 times my specific heat of, now it's liquid water, so 4,186, times my TF, minus what that started at, and my Q3 started at 0, so it's going to be minus 0, plus my ethanol of 2.5 times 2440 times, here, I'm just going to move this term right here. Okay, so this is going to be a plus 2.5 times 2040, because that's the specific heat of my ethanol, times the TF, which is what we're going to be solving for, minus what that ethanol started at, and it started at 20. That's all equal to 0. Q1, 7837.5. Q2, 83250. My Q3 is 1046.5 times TF minus 0 plus 6100 times TF minus 20, which is equal to 0. So now we're going to go through and distribute my TFs. So we get a 1046.5 times TF. And then we distribute this times 0, so it's going to be a minus 0. Then we distribute my 6,100 in TF, and we get 6100 times TF. And then we go through and we distribute that with the 20, and we get negative 1, 2, oops, that was supposed to be orange. And that's going to be minus 122,000, which is equal to 0. That should have been an orange as well. We combine all my TFs, which are in red, 7146.5 times TF. We combine all my non-TFs, which are the orangish color, and that gives us a negative 30912.5, which is equal to 0, which then we add that to the other side, and that equals 0, and we get a final TF of 4.32 degrees Celsius. So that's how you do these problems. If you have questions, please let me know. Otherwise, good luck with your homework and your quizzes.